I'll just jump right in. Although this is in some sense a continuation, I should take a moment to say thank you for having me. It was great for inviting me today. It's been very fun. I'm also coming at this from the perspective of a number theorist. I've heard about a lot of these problems for a long time. I'm very experienced in computation, but less so. Less experienced with actually applying machine learning. So this has been a very nice opportunity. A large part of this talk was actually motivated by something that came up in the talk this morning from Hay, which was Sarnak. He issued this challenge. He said, can you approximate or understand this really hard to understand function? And every once in a while people try, and this is another attempt. We have a new toy, and so I'll talk about this function. So the function I'm going to be looking at today is the Möbius function, u of n. It's 0 if the input n is square free, and otherwise it's plus or minus 1 depending on the number of prime divisors of n. Related to the talk earlier today, this is also related to the Lowry-Duda function, which tells you the number of different prime divisors. So that's the connection. For example, some things that you've never seen as Möbius function before. It's fundamental to number theory. To a number theorist, you look at this and you say, oh yes, it's a very nice thing, but it's also very confusing. We know it's sort of a hard thing when you're first learning number theory classes. You have to confront that this is often sort of the barrier to early analytic number theory. It appears in all sorts of places. It appears as the coefficients of the reciprocal Riemann zeta function. It appears in inclusion-exclusion arguments. It's very prevalent throughout number theory. It encodes all sorts of interesting things about prime numbers factorization. That's very deep. But despite being fundamental, actually studying anything about it's really hard. So there's this idea that in the prime number theorem, where you count the number of primes up to x, this is in some sense equivalent to knowing that the sum of the first x values of the Möbius function behaves asymptotically smaller than x. Not super obvious, but it's not so hard to actually see that this is how this works. In some sense, this is to say that the Möbius function doesn't correlate with the constant 1 function. We actually expect that the Möbius function doesn't correlate with any simple function, where I'm just going to brush aside what simple means. Or here, I guess I called it not too complex, in the sense that if you look at the behavior of the Möbius function multiplied by any not too complex function, we expect that it behaves, the resulting sum is small in terms of the weighting. This is one notion of Möbius randomness. A hard thing to really wrap your head around. But one thing that we suspect this means is that it's hard to find non-trivial correlations or predictive capability given the Möbius function. So these are the sorts of things that neural networks tend to actually do. They do some sort of correlative type behavior at a base level. So this is an obstruction. Can we overcome it? I'll note that the Möbius function, when you square it, this gets rid of the this gets rid of a sign. So when you square it, this is just always 1 if it's square free, and otherwise it's 0. So it acts as the square indicator function. So what this means is that the square free indicator function is just Möbius squared. It sounds much simpler than the Möbius function. In practice, it's also extremely difficult to compute. In fact, approximately the best algorithm we have to explicitly compute the Möbius function of n or the square free indicator function of n is morally to first factor n and then look. That's not entirely true. For example, if you're going to check for square free numbers, you don't have to find all the factors. If you don't have a square factor up to the cube root of n, then you're actually square free, for example. But morally, it's in the factoring type envelope. It's extremely hard. But okay, so we're going to try to learn this with machine learning. What should we expect? So first, if you look at the density of integers that are square free up to n, about 60% are square free, 40% aren't square free. And of the ones that are square free, about 50% have Möbius value 1, 50% have Möbius value -1. So what this means is that the absolute default guess should be, okay, if I'm just going to be given a random integer, do I guess if it's square free or not? You guess that it's square free, you'll be right 6% of the time. You're given a random integer, you want to know, well, yeah, that I suppose. Oh, and if you're given a random integer and you want to guess the value of the Möbius function, you have 3 choices that are roughly 40%, 30%, 30%. You should guess that it's always 0. You'll be right 40% of the time. So that's the boring, the most default level. But it's actually not so hard to write down a silly algorithm. The silly algorithm would be, okay, first look to see if 4 or 9 or 25, some squares of small primes, divide n. If so, output 0, and otherwise guess +1 randomly. This actually is already enough to get the square free indicator function correct 90% of the time. It's just one of those things where most numbers that are divisible by a square are divisible by a small square. I consider this not particularly interesting. To quote a talk that Jordan Ellenberg gave earlier in this program, this is an example where we can get to an algorithm which is 100% correct, almost, but somehow connotes 0% understanding of what's going on. And in fact, if you sit down and you just take out your favorite neural network, you open up your PyTorch, and you feed it in lots of n mu of n pairs, it will slowly always converge to the are you divisible by a small square indicator. And I don't want that. I'm looking for something more. This is sort of the goal of this was to, can we do something better that isn't just detecting divisibility by small squares? And so this is our guiding question. Our tool that we're going to use is the same tool that Andrew was just talking about, int-to-int, very kindly made for us and sort of guided through us with by François Charton. I should also give Edgar a lot of credit because Edgar, I wouldn't have been able to run this without all the work that Edgar put into it as well. So yeah, thank you, Edgar. So I shall also note, although I'm not going to talk about this in the talk, I ran many of the experiments I'm going to mention in a moment also on neural networks just to see if you get different behavior. And in practice, everything I say, you end up, a fully trained model gives about similar performance. But there's something special about this sequence transformer. It trains much faster, which is very nice. Anyway, so what sort of settings are we going to use? So think of this as a supervised translation task. I'm going to be choosing some representation of an input n that's not just giving in n. Because if you just give it n, you're going to end up converging to the same neural network behavior as before and detect are you divisible by squares of small primes. Don't want to do that. So we're going to be doing some different representation. We're going to be training this int-to-int, a sequence-to-sequence interval transformer model. We use cross entropy to measure our error. Transformers each have 4 layers encode and decode into 512 dimension sets, 8 attention heads per layer. Use Atom as our optimizer. These sort of standard machine learning type things that actually we just heard a second ago. More relevant to these experiments, so each experiment that I'm going to say started off with 10 million integers, uniformly sampled from integers up to 10 to the 13th. Without repetition, so there's no there. I separated testing sets and training sets, so they, as you do. So memorization is sort of an odd. Yeah, well, these are large sets, too large for the model to actually go. So how do you encode n to do an experiment like this? If you just feed in n, as we said, you're just going to end up getting a square free indicator function. But I want to learn something new. So try several different things. One thing that worked surprisingly well was using a Chinese remainder theorem type approach. In the Chinese remainder theorem, I feed in n mod p for the first 100 primes p thing. So you take n, you do n mod 2, n mod 3, n mod 5, so on and so forth. This doesn't uniquely determine n. It determines n uniquely mod the product of the first 100 primes. Of course, the product of the first 100 primes is far larger than 10 to the 13th. So we don't have any occlusion here. In some abstract nonsense, if this suddenly became a perfect predictor of the Möbius function, we'd have to wonder how that's possible. But it's not, I'll get a little bit ahead of myself. Turns out it's not a perfect predictor of the Möbius function. But this works pretty well. I'll note one particular aspect, which is that knowing n mod p, it's hard to determine, just given this, whether or not you're square free. Like even for a mathematician, if I just gave you this Chinese remainder theorem type representation and asked you, is this number square free? This is an interesting question that I think would be troubling. It's non-obvious. It was non-obvious. We'll hit this again later. But this is what I do. I also thought that it would be interesting to feed it the Legendre symbol. So this chi p of n, this is a number that is 1 if n is a square mod p. So for example, 2 is a square mod 7 because 3 squared is 9, mod 7 is 2. So this encodes square values, or whether or not something is a square mod p. There is a very clever algorithm for computing the Möbius function that's dependent on the generalized Riemann hypothesis for Dirichlet L functions, due to Andy Booker and his collaborators. And it uses Legendre symbols. And also, this is very obviously related to square freeness. So I thought that it might contain some additional information in it. Does it? No, it doesn't actually. In fact, so I originally had put down the plots including all 4, and then the behaviors are almost identical across all 4. So I just took a representative one. This is using just n and n mod p. I'm sorry, n mod p and p for the first 100 primes. And this is the sort of behavior that you get. So you start off with the trivial bounds. The trivial bounds were about 40% and about 60%, as we mentioned before. And then it very quickly learns for mu squared and then just stabilizes. And here it learns some 50% thing, which I understand, and then it learns if there's a sudden jump and gets up to about a little bit less than 60%, which I don't fully understand, but I sort of understand how it should work. I didn't think too hard about it, but for reasons there. And it turns out that including the Legendre symbols don't actually they don't carry a lot of additional information with respect to this problem, it turns out. So let's look more. How is it actually doing this? So let's take one sort of representative example of what the prediction table looks like. So one on a very good sample, it predicted 0 on approximately 3,600 of the 3,900 correct times. It sort of correctly predicted the right value 92% of the time. It was very good as a square free indicator recognizer. And then the other 2, it was bad. And actually, if I gave these prediction tables for lots of consecutive training models, it varied wildly between plus and minus 1. In fact, more generally, it couldn't really distinguish between plus and minus 1 at all. For this whole talk, every experiment that I'll talk about, I also attempted to distinguish between plus or minus 1, and in fact, they all failed. So fundamentally, the question of can I now predict the Liouville function or the sign of the Möbius function, the answer is no. But there's something that I still think is interesting here, which is why is it so good at recognizing squares? Well, I didn't quite know how this is going to work. Oh yes, so first, okay, what if I take away the option of being 0? I force it to predict either plus 1 or minus 1. So to do this, I only input square free n. Give it everything that you could, give it n mod p and the Legendre symbol. What does it do? And it just sort of hovers around 50%, never learns anything. This is true of all the models. It turns out I couldn't come up with any non-trivial correlative function. This isn't such a big surprise, but I do think that this should be formalized as a challenge. I joked with Jordan Ellenberg, who actually called it the Ellenberg challenge, because I've heard him talk about it a couple times, but instead I'll just call it the Möbius challenge. So train a model, any model that you want, any machine learning model that you want, with easy to compute inputs. Say they take at most their polylog n, and distinguish between mu of n is 1 and mu of n is minus 1, the probability greater than 50%. This is a great challenge, yeah.
And there's an information theoretic problem, which if you even try to learn the parity function, you put in n inputs, and you know that you're starting parity that only depends on k of the inputs. That's very hard. Just not information theoretic ground. This is like a parity.
Yeah, this is very much like a parity thing. I suspect, although I don't quite know enough of how this works in the background, this has to be morally equivalent. I mean, it's at least morally equivalent to the Möbius randomness conjecture without non-correlation. So presumably this is impossible, but maybe it's not. But maybe it's possible. We'll see. But why is it computing the square free indicator function so well? So let's return back to this interesting mathematical question. How would you as a mathematician actually try to compute whether or not n given n mod p is square free or not? Well, I think what you do is you just do the Chinese remainder theorem in reverse. You take, you'd figure out what n is, satisfying all the modular things, and then you'd use your favorite square function, trial division morally. That's a way that a real mathematician would do it. Is this what the machine's doing? So how do we figure this out? Well, let's set up new experiments. Let's see if we can understand what's going on. So, oh no, I didn't put my slide in one. This was all paused, so you get to see me say no lots of times. So just pretend that not all the dots are there. I emailed the wrong one. Anyway, is the transformer model doing the same thing that we would do? So first let's test the Chinese remainder theorem directly. Feed in n mod p. Can it get out n? Can it do this? No, but actually it's not surprising that it can't do this because the sort of the symbol space is just vastly too large. Using cross entropy. So this isn't a surprise. But that doesn't tell us that it can't learn data associated to the Chinese remainder theorem. Things that you would know if you were somehow encoding part of the Chinese remainder theorem within all your learned weights. So for example, suppose I split my interval, all my inputs were up to 10 to the 13. Can it identify whether or not n was in the first half of the interval or the second half of the interval? And it turns out it can't. So it's really, okay, so it's not doing some sort of approximation in the Archimedean sense of what the Chinese remainder theorem would give. Okay, well maybe in the p-adic sense. So if I give you n mod p, can it determine what n mod 4 is? No, so it turns out it can't actually extend this beyond further. I should note that during the workshop week 3 weeks ago, I ran an experiment here and said yes, and I don't understand why. And then I couldn't replicate it. So I lied. I must have set it up incorrectly. I don't know. Because I was like, oh my goodness, this is crazy. I have no explanation. Well, I really don't have any explanation. In fact, it was too good to be true. But no, so it doesn't know, can't learn mod 4, even mod 9, can't do mod 9 either. Okay, well, what if you omit a single prime? 2 or 3, can it recover n mod 2 or n mod 3 given the rest? No, it also can't. So it's the theme here that it's really not doing the Chinese remainder theorem. Well, that's surprising. But this last experiment was a big clue. So, okay, what if I use the second 100 primes instead of the first 100 primes? This is suggested by Drew. If there was some sort of Chinese remainder theorem type thing, maybe we would be figuring this out. And what happens? And it totally failed. Well, what if you go in the opposite direction? So let's instead feed it fewer primes. And in fact, I'm going to shortcut the fact that I did sort of an embarrassing amount of A/B type testing. What if I use just the first 2 primes? What happens? Oh, you end up getting 70%, just a little bit under 70% correct. Okay, this is actually somehow, this is disappointing in some sense, but it's also an interesting, a priori, I argue, an interesting mathematical claim. Knowing n mod 6 is enough to guess mu square, guess whether or not an integer is square free with probability about 70%. This is a concrete mathematical claim that, thinking about it for a couple minutes, not so hard to show, but I didn't recognize it beforehand. Right, and I talked about this problem with several people. We didn't initially see it. This is one of these things which in hindsight, I must admit, not hard. But foresight, it was very hard. And that's a useful tool. There is utility there. I'll return to that towards the end of the slide. So let's explain this prediction. So the claim is that knowing n mod 6 is enough to guess probability 70% whether or not n is square free. Despite the fact that n mod 6 doesn't tell you a whole lot about being square free. I mean, apparently it tells you 70%, but like just on the face of it, there are infinitely many cases where it isn't. That's easy to write down as many as you want. For simplicity, let's look even simpler. Let's just look n mod 2. So let's do a little exercise in probability. So I'm going to let the probability of SF be the probability you're square free, and 2 and 2 hat mean that you're divisible by 2 and not divisible by 2 respectively. So we want to know what the probability that you're square free is given that you're divisible by 2. This is sort of what the model's picking up on. Well, this is conditional probability. This is enough to figure out what are the probability of being divisible by 2 and 2. And in fact, it's just a correlation table question. Turns out that these are all explicitly computable. I've given here one sort of explanation for how you can try to figure this out. Okay, so what is the probability that you're both square free and divisible by 2? Okay, well, divisible by 2 means that you're at least you're congruent to 0 mod 2, but being square free means you're congruent to 2 mod 4. So that's 1 out of 4 conditions mod 4. Now you're square free for all the other primes. So you have 8 out of 9 possibilities mod 9, 24 out of 25 mod 25, and so on. You multiply all that together, you get a number. You get half of this number, because I multiplied by 2 already. You get 1/3 of zeta 2 inverse, just an explicitly computable thing. Whoops. And if you do not divisible by 2, you can also just explicitly figure out, you're just recovering this correlation table. So you get it turns out that if I give you a number and it's divisible by 2, and I asked you whether or not it is square free or not, if it's divisible by 2, you should say, it's already divisible by a small prime. It's probably likely that it's divisible by another small prime like 2 again. So I'm going to say it's not square free. It's probably divisible by 4. So that's what you guess. But if it's not divisible by 2, then you say, oh, that's one small prime, but it's not divisible by. I'm going to guess that it's not divisible by other, like the same small prime again, because that's how it goes. And this is correct with 40 or 80% of the time. So you put this together, what does this mean? So, okay, with so given an even n, this happens 50% of the time, you guess that you are square full. This is correct, as we just said, with probability 1 minus the 0.4 number, which is about 0.6. Otherwise, say that it's 1, which is correct with probability 0.8. Add these together, you get 72% of the time. So that's actually all that's picking up. An easy exercise, but a non-obvious exercise. So a similar calculation using only the prime 3, not prime 2, gives you an algorithm that's correct 63.7% of the time. And more generally, if you want to know like how this sort of works, this is the total probability thing. Each of these are prime divisibility things are completely separate restrictions. So you can just explicitly work out what the correlation table would be. And it's not a surprise that machine learning picks up on correlation tables. But what is a surprise is that the correlation tables weren't uniform. That's what I hadn't realized. So in hindsight, we should have expected this. And really what happened is that I, as a number theorist, was coming at this from the direction of thinking that I want to compute mu of n. I'm trying to use this machine learning model to compute mu of n, but it's not computing mu of n, it's predicting mu of n. So it's just, it has access to these huge correlation tables, and this is what you do. I'll note that I almost included the math for how it was trying to get to 60%, but it's more complicated because it turns out that, so in the background, this is essentially a Bayesian classifier that's sort of is being encoded. For the simple model here, there's no weights. It's either you're in this class or you're not in this class. But it turns out that when you're looking at mu of n instead of the whole squares, you actually include non-trivial weights. And so presumably the second bump was at learning a non-trivial set of weights that worked well. So from afar, this actually looks similar to the initial neural network experiments done by Ellenberg earlier. When you train n and the square free indicator function with a neural network, what you learn is the are you divisible by a small square of a prime function. And somehow what we've learned today is are you divisible by a small prime function. Okay, but I think this is actually unkind. What really happened is that we did some experiments, we did some A/B testing. This was a small transformer that we could train and iterate on lots of times, and I learned something. And that's sort of what we're trying to get out of this anyway. I'll also note, Noam isn't here. So I talked about this with several people here for a couple of days, I don't know, for like half of that workshop week. And then someone mentioned this to Noam, and I'm pretty sure that Noam immediately said, oh, being odd square free is twice as likely as being even square free. And I said, oh, wow. So in some sense, what int is doing is it's sort of acting like a pocket gnome. And that's very powerful. That's an extraordinarily powerful thing. That's great. But yes, and more generally, this fits into sort of a particular way that I find int and other transformer models interesting and applicable even to a computational number theorist type thing, which is I have a pile of data, I have a pile of inputs. I'm trying to determine whether or not it carries explanatory power about the outputs. It's sort of a one-sided oracle. Sometimes it says this data does in fact contain lots of information about the output. That's great. If it fails, that doesn't tell me that the information is not there. This is the sense in which it's one-sided. And it's an oracle because it can't explain its premonitions from the data. But nonetheless, when it comes up with a positive thing that says information is there. And this is a very useful thing. As we were saying in the talk just before, the information about A97 is there. How is that happening? I don't know. This is very interesting. So what I learned from this set of experiments is that these actually are useful tools. They can point us to interesting directions. And I'll stop there. Thank you.